Okay, let's unpack this. If you've ever taken an introductory statistics course, I'm willing to bet there was one mantra, one phrase that was just drilled into your head above all others.
Oh, absolutely. The big one.
The big one. Correlation does not imply causation. But for, a working analyst, or just a curious learner, or frankly, anyone trying to make sense of a headline, that simple phrase is, well, it's both the key to wisdom and, if you misunderstand it, the source of some immense analytical frustration.
It truly is foundational. I mean, we see this concept misused everywhere in policy debates and investment analysis, public health reporting.
Everywhere.
So our mission today is really to move past just saying the phrase and to give you a rigorous toolkit for separating genuine influence from what is, in the end, mere coincidence. If you can master this distinction, you will instantly become a far more objective interpreter of data.
That's the goal. Because the natural impulse, even for researchers, is to assess correlation precisely because they suspect a causal link is there. They run the numbers, they find a strong, a statistically significant association, and the temptation to just declare A causes B is overwhelming.
And that temptation, that sort of cognitive shortcut, is precisely what leads to so many flawed conclusions. Finding a strong association is simply not enough evidence to secure a causal claim. The problem isn't the data itself. The problem is the reasoning we use to interpret it.
So let's start with the basics, just to give ourselves the necessary clarity. What exactly are we talking about when we discuss correlation?
Correlation is strictly a measure of statistical association. It just quantifies how two variables move together. We're looking for a linear relationship, and we measure it using something called the correlation coefficient, which is symbolized as a lowercase $.
And that total value is so useful because it immediately tells you two things, right? The strength and the direction of that relationship. It runs on a scale from +1 to -1.
Correct. So when $3 is close to +1, we have a positive correlation. This just means the variables are moving in lockstep. They both increase together, or they both decrease together. The classic textbook example is always something like the number of hours you studied and your exam score.
More hours, higher scores.
Exactly. More hours, higher scores. And if $3 is closer to -1, that indicates a negative correlation.
Meaning they move in opposite directions.
That's right. As one goes up, the other tends to go down. If we look at, say, a product's price and the consumer demand for it, generally, as the price goes up, the demand goes down. And if $3 is near zero, we just conclude there's no real linear relationship between them.
Okay, so that's association. Now, setting that aside, what is the hard statistical requirement for causation?
Well, causation requires a definitive cause and effect relationship where a change in one variable, let's call it $6, directly influences or brings about a change in another variable, numbers dollars. The technical definition is that $6 causes if, and only if, 6 and dollars are correlated under interventions on $6.
Ah, that last part. Under interventions. That's the key.
That is the key. You have to show that when you actively go in and manipulate $6, the change reliably follows in dollars. It's not just about watching them move together.
And that distinction, the passive observation versus the active intervention, is what generates that fundamental rule we all know. Causation always implies correlation, but correlation does not imply causation.
And we should probably clarify that word imply because it confuses a lot of people. In everyday language, imply kind of means suggests or hints at. But in logic and statistics, imply is technical. It means is a sufficient condition for.
Okay, so if I'm understanding the technical language, when a statistician says correlation does not imply causation, what they're really saying is that the mere existence of a correlation is not a sufficient condition to guarantee a causal relationship.
Precisely. It is always, always technically correct to state that correlation does not imply causation because correlation alone is never enough to secure that causal claim. I don't care how strong that Toradol value is. It's a necessary condition, but it is never a sufficient one.
Okay, that sets the stage perfectly. So if correlation is just the beginning of the story, what are the plot twists? If we find a strong association between our 6-day span and our dollars, what are the three main alternative scenarios we have to methodically rule out before we can even begin to claim that $6 cause dollars?
These three alternatives are really the analytical framework you have to adopt anytime you're looking at observational data. If you can rule them out, your causal argument gets substantially stronger. If you can't, well, your claim is weak.
The first one, and I think the most insidious, is that lurking factor, the common causal variable, often called a confounder. Let's label it totaler.
This is the mechanism that generates the most misleading correlations. The confounder, $6, is something that influences both $80 and dollar independently. So since $8 and $80 are both moving as a result of Toller, they appear statistically related to each other, even when they have no direct causal link whatsoever. We're just seeing parallel effects.
Right, this is where we usually talk about the classic ice cream and shark attacks example.
Yeah.
But for our audience, let's use a more complex, sort of contemporary example that I think reflects the difficulty of real-world research. Let's look at the correlation that's often found between, say, high social media use, that's $8, and increased rates of depression, basal dollars, among teenagers.
Oh, that's an excellent one because that correlation is consistently found to be moderate to strong in studies. And initially, headlines will jump straight to the causal conclusion: social media scrolling causes depression.
Of course.
But the data analyst has to immediately stop and ask, what is the common variable? Dollars. What could be causing both?
And dollars could be anything from genetics to their home environment. I mean, maybe dollars is a general disposition towards social isolation, or maybe a pre-existing anxiety disorder.
Exactly. A teenager who's already struggling with social isolation, that's our dollars, might seek out the online world more aggressively, that's our dollars, and that exact same isolation is already a known driver for depressive symptoms, our dollars. If that's the case, social media isn't causing the depression. The underlying isolation is causing both the increased social media use and the depression.
So the relationship A causes B it's entirely spurious. And that brings up the really terrifying part about confounding variables, which is just the sheer number of them.
The problem for any analyst who's relying purely on observational data is that the number of variables that could potentially be the dollars is, mathematically, it's functionally limitless. If you're just watching the world go by, you can never be certain you have identified and controlled for every single factor.
Could you elaborate on that, on the practical difficulty of this limitless problem in something like, say, a public policy implementation?
Certainly. Think about a city government. They implement a new public transit system that's $6, and they see a correlation with a subsequent rise in local economic activity. The city, of course, wants to claim our new transit system caused this economic boom. But what are the potential confounders, the C's? Did the city also simultaneously offer massive tax breaks to attract new businesses? Did a huge, unrelated tech firm just happen to open a new campus nearby? Did national interest rates drop, making it cheaper for everyone to invest locally?
Right. You're measuring the effects of your transit system, $6, alongside potentially dozens of other concurrent macroeconomic and political decisions, all of which are C's.
And unless you can properly design an experiment to isolate $6 from all those C's, which you can't because policy decisions are not randomized, you are simply observing a correlation that is likely being driven by several powerful common causes all at the same time. And that's why governments often struggle to prove the efficacy of any single large-scale investment.
We really have to revisit Simpson's paradox here as well, because it's such a perfect visual for how a single, powerful confounder can completely flip a conclusion on its head.
This is so critical for data analysts who rely on aggregated results. We discussed that simulation involving foot size and reading scores. If you just pool all the data on children from, say, ages 5 to 15, you see this really strong positive correlation and $3 at about 0.75. The overall group data is screaming, bigger feet, better readers.
But the moment you split the data by the confounder, which is age, the correlation just vanishes.
It's gone. Exactly. When you look at only the 5-year-olds or only the 10-year-olds, the relationship between their foot size and their reading ability is statistically zero. The entire misleading association was created just by the aggregation. Age drives both variables simultaneously, and if you aren't aware of that confounder, you will draw a false yet statistically validated conclusion from your pooled data. This happens all the time in things like salary analysis or medical efficacy trials when patient groups are improperly mixed.
So even if we diligently search for confounders, we still have the problem of directionality. We see A and B correlating, and our human brain, it just instinctively defaults to A causes B. But what if the influence is actually running backward? What if B is causing A? That's reverse causality.
This is a pitfall that's born from measuring A and B at the same time, or just failing to track the precise timing of events. That loyalty program analysis we discussed is a great way to illustrate this reversal.
Right, so the initial correlation was high customer ratings, that's A, were associated with high visit frequency, B.
And the initial, the intuitive hypothesis was better service leads to satisfaction. Our A and satisfied customers visit more often, our B. Makes sense.
Seems plausible.
But the analysts investigated further, and they found that customers who visited more often were more integrated into the loyalty system, they had more experience with the staff, and they had more repeated opportunities to give feedback.
So the frequency itself was the driver of the satisfaction rating.
Yes. The frequency, B, led to familiarity and a higher likelihood of them responding positively, which is A. The direction of the causal arrow was actually B leads to A. If the loyalty program managers had spent millions trying to boost satisfaction scores, believing that would increase frequency, they would have completely wasted their money because the frequency was already driving the satisfaction.
This issue of timing must be even more acute in medical research, where a condition might start changing a person's behavior long before a diagnosis is ever made.
Oh, absolutely. The orthopedic research example is really potent here. We look at physical activity, let's call it $6, and the longevity of a joint replacement, $8. Now, a simple correlation might suggest that highly active people have replacements that last longer. However, if that patient's replacement is secretly starting to loosen, which is the eventual outcome, they will instinctively reduce their physical activity, $6, because of the pain, long before a revision surgery is even scheduled.
So the imminent failure of the implant is actually causing the reduction in activity.
Precisely. If we measure their activity too late in the game, we see low activity correlated with impending failure, and we might spuriously conclude that high activity is protective. But in reality, the onset of the outcome is reversing the exposure. Researchers have to use really sophisticated follow-up protocols or analyze very early patient data to avoid this kind of misleading reverse causation.
And that brings us to our final alternative, which is the simplest, but maybe the one we need to be most skeptical of, especially now in the modern age of big data.
Mm.
The relationship is purely random. It's just a statistical coincidence.
This is where we have to acknowledge the powerful evolutionary drive of human pattern recognition, or the technical term is apophenia. We are just wired to find connections because historically, finding a connection between two events like I ate this type of berry and now I have a stomach ache was key to survival. But today, that same instinct makes us highly vulnerable to false positives.
And when you couple that deep-seated bias with modern data mining techniques, the problem just scales up exponentially.
Absolutely. Think of it this way. If you measure 100 random variables every single year for 20 years, you've got thousands of data points. If you then test every single possible pair for a correlation, statistical chance alone dictates that you will find hundreds of statistically significant correlations at the standard 5% confidence level just because of random noise.
The famous spurious correlations websites, right? The one showing Nicolas Cage films correlating with drownings in pools or cheese consumption correlating with stock prices. They're hilarious precisely because they visually demonstrate this principle so well.
They show us that correlation is purely a numerical relationship that exists completely independent of any real-world mechanism. No amount of cheddar is influencing BlackRock's balance sheet. And we should pause on that absurdity for a moment because it's the most powerful lesson in statistical humility. If you look hard enough, you will find nonsense correlations that look compelling on a graph.
And this feeds directly into our own cognitive biases. You mentioned confirmation bias and the illusion of causality.
Right. If you already believe the world is moving in a certain direction and you find a correlation that supports that belief, you will naturally stop digging. You won't look for confounders or reverse causation. This is confirmation bias in action. And the illusion of causality is when you allow personal anecdotes or just a powerful story to override the statistical likelihood of coincidence. An analyst has to constantly fight that urge to confirm what they already suspect.
So we've established that just observing the world is flawed. If we can't simply observe our way to a causal conclusion, how do scientists and analysts actually move beyond the starting line of correlation to the finish line of causation?
We have to move from passively watching the world to actively experimenting on it. We have to enforce the conditions required to isolate the effect of one single variable.
And the undisputed gold standard here is the randomized controlled trial, or the RCT. Why is randomization such a powerful tool in establishing cause?
The power of the RCT lies in its ability to handle that limitless problem of confounders we talked about. By randomly assigning your subjects, whether they're people, products, marketing campaigns, to either a treatment group, the one that gets $6, or a control group, the one that gets a placebo or no $6, we are statistically ensuring that all known and, crucially, all unknown pre-existing individual differences are balanced out between the two groups.
So if we have enough subjects in the trial, we can assume that the average genetic background, the average socioeconomic status, the average personality type, all those potential unmeasured Cs are roughly equal in both groups.
Exactly. When the groups are comparable in almost every way, any subsequent difference we measure in the outcome, dollars, can be attributed, with very high confidence, only to the intervention, $6. Randomization is the ultimate technique for controlling for the unknown.
And as we noted, it also automatically solves the reverse causality problem by establishing temporal precedence.
Precisely. We actively administer the treatment, $6 at time 1, and we measure the outcome, chems, at time 2. The cause must precede the effect. So if a difference in the outcome is found, we know that the outcome couldn't have caused the treatment because we administered the treatment first.
And this isn't just a theory for pharmaceuticals. This framework, as we mentioned, is really the backbone of modern tech and business analytics.
Oh, absolutely. Think about the complexity of a global streaming service that's performing A/B testing. They want to know if adding a tiny little animation to their subscribe button increases conversion rates. They don't just guess, they run an RCT. Millions of users are randomly split. Group A, the control, sees the old static button, and Group B, the treatment, sees the new animated button.
And if Group B shows a statistically significant lift in conversions, they can then causally attribute that lift to the animation.
Yes, because they have isolated that single variable while controlling for everything else. The time of day the user logs in, the user's location, their device type, their past viewing history, all that background noise gets balanced out by the randomization. The causal claim is robust. I will say, though, a key caveat with RCTs is that while they have high internal validity, meaning they prove causality within the experiment, they can sometimes suffer from low external validity. How well the results actually apply to the real messy world outside the controlled conditions.
So when RCTs are impossible, we still have to be meticulous about timing. A fundamental step in moving toward any causal claim is just verifying that the purported cause happens before the effect.
It is a non-negotiable requirement. In fields like microeconomics, where we're dealing with these complex systems we can't possibly randomize, this temporal check often involves very sophisticated time series analysis to model the lead-lag relationships between variables.
So let's deepen our understanding of that interest rates and inflation relationship, because it's constantly debated in the news.
Right. We know that central banks raise interest rates, that's $6, with the intention of cooling down inflation, dollars. Now, if the rates truly cause the drop in inflation, we need to see a reliable lag. Analysts will look for confirmation that inflation consistently decreases, say, 4 to 6 quarters after a rate hike. The stronger and more consistent that lag is, the stronger the causal evidence becomes.
But the timing often confuses people, because central banks are, by their nature, reactive.
Exactly. If your time series shows that inflation spikes consistently precede the rate hikes, well, you have definitive evidence of reverse causation. The central bank isn't causing anything in that moment. They are simply reacting to the market signal. They are the effect, not the cause, in that immediate relationship.
And when inflation is high, the market is just extremely noisy.
That's the core difficulty. I mean, during the post-2022 inflation surge, inflation did ease significantly, but was this purely the causal effect of those interest rate hikes? The source material we have suggests the data is far more complicated. We have to consider massive confounding factors.
Such as what?
Well, global supply chain resolution. That was the primary cause of many of the price spikes, and those issues resolved naturally independent of U.S. interest rates. Commodity prices, especially for energy, dropped significantly due to geopolitical shifts. And then you have changes in fiscal policy, government spending, which were massive and concurrent.
Right.
So it is, frankly, intellectually lazy to just plot two variables on a chart and declare causality when you have dozens of powerful, non-randomized forces acting all at the same time. The correlation in timing was high, but the proportion of that inflation cooling that can be causally attributed to rate hikes is fiercely debated by economists using these advanced causal inference models.
So since we can't run RCTs to study many critical issues, like the long-term impact of poverty or the effect of salt intake on hypertension, researchers have to get creative. They have to move into this field of causal inference to try and extract meaningful causal conclusions from messy observational data.
This is where we use statistical ingenuity to try and mimic the conditions of an RCT. And the prime example of this is the instrumental variable method, or IV.
Okay, this sounds complex. Can you give us the technical definition first and then maybe an analogy?
Sure. Technically, the instrumental variable is an external variable, we'll call it Zähler, that influences your exposure, 6 spike, but can only affect your outcome, through $6. And crucially, this instrument, Zeller, has to be independent of all those pesky confounders, the C's, that influence dollars. So we use Zeller as a kind of clean, unbiased proxy for $6.
Okay, so let's say the exposure is smoking, $6 and the outcome is lung disease. We can't randomly assign people to smoke. So what would be the instrument, the Zeller in that case?
This leads us to a really powerful type of IV called Mendelian randomization. This technique uses genetic variants, or SNPs, as the instrument. We know that certain genetic variants are associated with a greater tendency to smoke heavily. Since these genetic variants, our Zeller, are randomly assigned at conception, they are naturally independent of lifestyle or environmental confounders like C.
Ah, so genetics is providing the randomization that we can't get from a clinical trial.
That is a perfect way to put it. We are using nature's randomized lottery, the distribution of genes, to create a proxy exposure for smoking quantity. This method provided strong, relatively unconfounded evidence linking smoking to various health outcomes. In that orthopedic research example we mentioned, Mendelian randomization actually challenged previous observational findings by suggesting a causal link between smoking quantity and a reduced risk of osteoarthritis, which really highlights how traditional observational studies might have been misled by factors like BMI or socioeconomic status.
And we're also seeing these techniques accelerate now into the computational domain with what's called causal AI methodology.
Causal AI is really the modern evolution of this same line of thinking. Traditional machine learning is excellent at prediction, saying if I see A, B, and C, then Y is likely to happen. Causal AI, however, is aimed at explanation. It wants to say A is what made Y happen.
And the real power here is in addressing those hidden, the unobserved confounding factors.
That's the real frontier. In any complex business or clinical setting, you always have hidden factors. For example, a causal AI system that's analyzing drug trial recruitment might determine that the observed increase in patient enrollment wasn't actually caused by the new, aggressive digital ad campaign, the known $6, but instead by an unobserved change in a competitor's market activity, a hidden dollars. Causal AI uses these sophisticated techniques to infer the presence of those hidden factors and then adjust the causal estimate of the known variables accordingly. It moves us closer to simulating counterfactuals. What would have happened if we hadn't done $6?
Okay, now let's briefly address the highly theoretical, but I think fascinating challenge to our core rule. We stated that causation always implies correlation. But are there extreme theoretical systems where a causal link exists, yet the statistical correlation is literally zero?
Yes, this can occur in very specific, purely deterministic systems, often studied in theoretical physics or information flow theory, that possess a certain kind of symmetry.
Give us the high-level concept if we can, avoiding the really heavy math.
Okay, imagine a perfectly symmetrical, nonlinear system where A definitively causes B. For instance, think of a variable whose movement is strictly cyclical, like a sine wave. If you calculate the standard linear correlation coefficient, $4 over a full period of this perfect cycle, the result can actually be zero.
Why?
Because the positive deviations from the mean in the first half of the cycle are exactly canceled out by the negative deviations in the second half.
So the correlation coefficient, which is really just designed to measure linear association, it completely fails to capture the causal relationship because the relationship is deterministic, but it's nonlinear.
Precisely. The linear correlation is zero, despite a clear causal link. It doesn't mean the causal link is absent, it just means the standard statistical tool we use to detect it, the correlation coefficient, is inadequate for that specific structure. The contradiction gets resolved by moving beyond simple covariance and calculating the normalized information flow rate between A and B, which would confirm the 100% causal influence, even when correlation fails. It's a key reminder that statistical models are just approximations, and they have blind spots when dealing with perfect nonlinearity or pure determinism.
That technical discussion was essential to understand the limits of our tools. So now let's bring it all back to real life. Why is it so dangerous to mix these concepts up in high-stakes domains like health and economics?
Public health is a perfect crucible for this debate because it provides us with both validated causation and catastrophic misinterpretation. When theory, mechanism, and correlation all align, we can have the highest confidence.
And the introduction of the polio vaccine in the 1950s is a textbook success story here.
It is. Polio was a terrifying scourge. The Salk vaccine was introduced, and the correlation between a vaccine uptake and the collapse in case numbers was just dramatic. Cases plummeted from over 58,000 annually to just 5,600 in 2 years. The timing, the magnitude, and the underlying biological mechanism, the vaccine generates immunity, It all aligned. The compelling correlation confirmed the hypothesized causation.
Now, contrast that with the infamous autism false correlation.
This was the opposite case, where fear completely trumped analysis. The false claim, which we now know was based on fraudulent data, found a correlation based purely on coincidental timing. Children receive the MMR vaccine around the same age that parents typically begin noticing the first signs of autism.
So you have a simultaneous recording of two events.
Exactly. The correlation was a product of the human lifespan and the typical diagnostic schedule, not a biological interaction. And decades of subsequent research have failed to find any causal link whatsoever.
But the societal damage was done. That initial spurious correlation drove a massive change in parental behavior following vaccination rates, which tragically revealed a terrifying true causation.
Explain that feedback loop.
Well, when vaccination rates fell below the necessary herd immunity threshold, for example, dropping below 80% in parts of Great Britain, measles, which had been virtually eliminated, roared back as an epidemic. So this provided a real-world, albeit tragic, experiment. It demonstrated definitively that the lack of vaccination was causally linked to higher disease incidence. The correlation of lower vaccination and higher disease prevalence tragically revealed the true underlying causation of disease spread. A false correlation led to a behavior change that proved a true, devastating causal relationship in the opposite direction.
Macroeconomics constantly struggles with this issue because the variables are just so massive and interdependent. The notion that rising interest rates cause falling inflation is treated as an article of faith by some.
And it's true that they often correlate, but this correlation is frequently due to simultaneous reactions to large shared factors. Let's focus on the 2022 to 2023 inflation cycle. Central banks raised rates aggressively, that's $6, and inflation did ease, that's dollars. The causal narrative was immediately established in the public consciousness.
But the analyst has to look deeper. What else was happening in the background?
Massive confounding factors. First, consider the supply shock resolution. Inflation began spiking in 2021 because of all those COVID-era supply chain bottlenecks and factory closures. By 2023, those issues had largely resolved themselves. Ships were moving faster, ports were unclogged, factories were back online. This disinflationary force was completely external to interest rates.
So inflation was falling naturally anyway, meaning the correlation between falling inflation and rising rates was just coincidental timing?
Correct. Second, commodity prices. The energy price surge after the invasion of Ukraine eased in 2023. Lower oil prices reduced the cost basis for nearly every good and service globally, which pushes inflation down again, largely independent of central bank rates. And third, consider fiscal policy and consumer expectations. That massive government pandemic-era spending created a surge in demand. As that spending waned, demand naturally cooled.
So the narrative that the Federal Reserve single-handedly engineered the soft landing, it really ignores the massive tailwinds from supply chain resolution and falling oil prices.
Precisely. When economists use advanced time series modeling to tease apart these factors, they often find that the immediate causal impact of the interest rate hikes on inflation is actually weaker and slower than the public narrative suggests. The observed correlation in the charts is visually compelling, but the true causation is distributed across multiple, high-powered, independent variables. This really reinforces why just plotting two time series is incredibly misleading unless you apply advanced controls.
We stress this phrase, correlation does not imply causation, so heavily that sometimes the message gets a little distorted. We risk training analysts to dismiss correlation entirely.
This is a major concern. Analysts, having been trained to spot the false cause fallacy, sometimes make a second-order error. They incorrectly conclude that a causal relationship cannot exist among correlated variables. They start to treat any correlation as tainted and irrelevant.
Which means they ignore valuable clues.
Exactly. If you only present absurd examples like the Nicolas Cage scenario, you train your audience to think correlation equals nonsense. But in high-stakes fields like climate modeling or studying the link between early childhood intervention and adult outcomes, you simply cannot run an RCT. You are relying on strong, repeatable correlations.
So we need to reframe this for the savvy consumer of information. When you see a strong correlation reported in the media, the proper response isn't, oh, it's only correlation, so I'm dismissing it.
The proper response is, okay, this is a strong finding. It forms a robust hypothesis that may be causal. Now, what are the most likely confounders, and what is the direction of influence? Can I find other studies that use stronger methods like IVs or RCTs to confirm this mechanism? You move from dismissal to critical investigation. Correlation is a valuable signal, provided you treat it as a starting line, not a finish line.
So let's pivot to the positive role of correlation. When direct experimentation is impossible, scientists don't just throw out their data, they use correlation as a map to build a complex, plausible story of causation.
Correlation is the indispensable first step. It generates the hypothesis that guides all future research. The key is what scientists do next. They test the robustness of that correlation by constructing what you call a plausible web of connections.
So what does it mean to test the robustness of a correlation?
It means moving beyond a single study in a single location. Scientists stress test the correlation by asking these crucial questions. Is this correlation repeatable across different studies? Does it hold in different geographical locations with different populations? And most importantly, when we use statistical methods to control for a wide array of observable external factors, things like pollution levels, nutrient density, ocean temperature, does the correlation still persist?
If the relationship survives all of those stress tests, even if it is still technically only a correlation, it becomes much more compelling.
It gains scientific weight. It moves from random noise to valuable clue. We move from simple association to thinking about the underlying physical or biological mechanism.
So let's use the complex example of the ecological cascade of otters and erosion to show how scientists can stitch together these plausible webs when a system is just too massive and complex for a lab setting.
This is a fantastic illustration because it links 19th century human activity to modern coastal geography through a chain of verifiable strong correlations. It's really a story of indirect causation.
The story begins with historical human behavior. So correlation 1. Otter pelt hunters leads to a drop in the otter population.
This is a very robust inverse correlation, right? It's supported by historical records from the maritime fur trade. It's a, 9 out of 10 plausibility? Humans nearly hunted the sea otter to extinction in the 18th and 19th centuries.
The disappearance of the otters then led to the explosion of their primary prey. So correlation 2. A drop in otter population leads to a rise in the sea urchin population.
And this is a core ecological principle, a keystone predator relationship that has been tested and demonstrated countless times. When you remove the predator, the prey population explodes. That link is a 10 out of 10 plausibility.
The urchin explosion then correlated with a decline in marine vegetation. Correlation 3. A rise in the sea urchin population leads to a decline in the health of kelp beds.
And urchins are grazers. When their population is unchecked, they consume huge areas of kelp forest, turning them into what ecologists call urchin barrens, another 10 out of 10 plausibility.
Now we get to the geographic outcome. Correlation 4. A decline in the health of kelp beds leads to a rise in the rapid erosion of the California coastline.
This is the final, maybe slightly weaker correlation, perhaps a 6.5 out of 10 plausibility. Kelp beds act as these massive natural buffers. They reduce wave energy and stabilize nearshore sediment. When they disappear, the coastline is exposed to much greater kinetic force from the ocean, which accelerates erosion.
So we have this complex causal narrative where 19th century fashion trends, like otter shawls, are causally connected through 4 intermediary, well-tested correlations to modern coastline stability. We didn't need one giant, impossible RCT.
No. We needed domain knowledge, careful observation, and the statistical rigor to confirm each individual step. The overall plausibility of that entire chain, despite its reliance entirely on observational data, is rated very high, maybe 8.5 to 9 out of 10. It shows that correlation, when it's chained together with other validated correlations, can build a powerful case for complex causation.
And this emphasizes the danger of the opposite fallacy. The intellectual dishonesty of entirely dismissing correlation because it isn't causation, especially when the findings are politically or economically inconvenient.
This fallacy has historically been weaponized by vested interests to sow doubt and defer action, even when the correlational evidence is overwhelming and pointing toward an unavoidable conclusion.
The history of the tobacco industry is just a stark example.
The tobacco industry spent decades arguing that the clear, consistent, overwhelming correlation between smoking and lung cancer was merely correlation. They leveraged the principle that only an RCT could prove causation. And since it's completely unethical to run an RCT where you assign children to smoke cigarettes for 30 years, they argued that the causality was never truly proven.
But the correlational evidence arrived from multiple independent angles, from epidemiology, pathology, and eventually molecular biology.
Precisely. And while one correlation doesn't prove cause, a correlation that appears from multiple methodologically diverse studies is powerful evidence for a causal hypothesis. Moreover, correlation, even without definitive proof of cause, is still incredibly useful for prediction and for policy. If you know that A and B reliably move together, you can predict B's movement based on A's, which is critical for planning, even if you don't know the exact mechanism.
For example, if social researchers find a strong, repeatable negative correlation between socioeconomic status and academic outcomes, even if they can't run an RCT to prove poverty causes lower scores, they must still use that correlation for resource allocation and planning interventions. Dismissing it as just correlation would be completely irresponsible.
This has been an intensive deep dive. We started by defining correlation, the dollar value, versus the rigorous requirement of causation, which is correlation under intervention. We detailed the three major pitfalls: the functionally limitless problem of common causal variables or confounders, reverse causality, and the inevitable risk of coincidence when you're data mining.
And we highlighted the methodological path forward, the gold standard of the RCT, the non-negotiable step of temporal checks, and advanced causal inference techniques like instrumental variables and causal AI, which provide researchers with the ingenuity necessary to tackle causality in observational data. We ended with the crucial realization that complex problems often require stitching together these plausible webs of correlation, like the otter kelp story, rather than relying on a single, isolated result.
So we know that as humans, we are fundamentally hardwired to look for causal structure. It's essential for our survival and for controlling our environment. But we also know that in massive, complex, high-stakes domains like long-term behavioral effects, climate change, or global economics, rigorous experimental evidence is often impossible to obtain.
Which forces us to rely on assembling those plausible webs, driven by deep domain knowledge and testing for multiple strong correlations. And this leaves us with our final provocative question for you. In complex, high-stakes domains where intervention is impossible, should we place greater trust in a carefully constructed multi-step chain of strong correlations where each link is supported by plausible domain knowledge, or should we exclusively trust a weak, isolated result from a single observational study, even if that study claims to have statistically controlled for a few variables? How do we balance the pure statistical rigor against the urgent human need for a compelling, actionable story about the world? That is the analytical challenge for all of us today.